Hello and welcome, class, to the conclusion of Chapter 8. Yes, that is right, the conclusion of Chapter 8. It really is, again, a short chapter, so it's, the way I delivered is really in like a 1-2 punch. So part 1 was balancing chemical equations, and now here in part 2 we are going to use those balanced equations in order to see how we can really make sense of like data gathered in lab pertaining to chemical reactions via stoichiometry and a calculation of the percent yield. So what is stoichiometry aside from being an excellent word to use in Hangman or Scrabble? Well, stoichiometry pertains to the coefficients in a balanced chemical reaction, which again we learned how to place in the previous lecture. The coefficients in a balanced chemical equation indicate both the relative numbers of molecules that go into a chemical reaction, but also if we scale up via Avogadro's number, the coefficients also pertain to the relative numbers of moles in a chemical reaction. So for instance, if we observe the decomposition of water into hydrogen and oxygen, what this equation at like surface level tells us is that 2 molecules of water will break into 2 molecules of hydrogen and 1 molecule of oxygen. Macroscopically, again, if we scale by Avogadro's number, this is the equivalent of saying 2 moles of water break up into 2 moles of hydrogen and 1 mole of oxygen. So if we then actually perform the chemical equation of breaking up water, which we can see in this vessel here on the right, it takes zapping it with electricity, so we're going to add a battery or a voltage source. What we end up seeing is as the water comes in, H2O in, we end up with 1 part oxygen gas on the left-hand side here, and 2 parts hydrogen gas on the right side here. This is a 1 to 2. We can conclude this because the volume of gas is twice as large, meaning that we have twice as much hydrogen as what we have oxygen, and that matches what we see in the chemical equation, 2 parts hydrogen and 1 part oxygen. So macroscopically, we can use this chemical equation to make some predictions not only about how much water goes in, but also about how many products we would expect to see even before performing a chemical reaction. And the way that I'm going to be teaching the use of stoichiometry in this way is by, making a parallel analogy to cooking. Because really, what is following a recipe if not following a detailed chemical equation for the combinations of foods? For instance, down below, I have rewritten a recipe for making pancakes into a form of a chemical equation. If we take 1.5 cups of flour, 1 tablespoon of sugar, 3.5 teaspoons baking powder, 1 teaspoon salt, 1.25 cups milk, 3 tablespoons of butter, and 1 egg, blend them up in a bowl, bake them on your, stovetop or on your griddle, you should get 10 pancakes on the other side. So this chemical equation, mixing up all of our reactants, which are all of our ingredients, and the creation of our 10 pancakes or 10 products is like a chemical equation. Now we can also ask ourselves, well, what happens to this recipe if we actually have, for instance, 3 cups of flour? Well, provided we have enough of the rest of the ingredients, we can look at how many cups of flour the recipe normally takes. We can see 1.5, and we can intuit, well, 3 is just equal to 2 times 1.5. So if we have 3 cups of flour, which is twice as much flour as what we need, 3 cups of flour then would mean that we would need 2 cups of table sugar, 7 teaspoons of baking powder, 2 teaspoons of salt, 2.5 cups of milk, 6 tablespoons of butter, and 2 eggs, and this would make 20 pancakes. Right, so if we have twice as much flour, assuming that we also have twice as much of everything else, we get 20 pancakes on the other side. This is manipulating the chemical equation via stoichiometry. You get you want to put twice as much in, you get twice as much out. Or conversely, if let's say it's only pancakes for 1, you don't want to have too many leftovers, so you scale down the entire equation the entire recipe to only make 5 pancakes. Let's clear this off. We only want to make 5 pancakes. That means that it looks like, relative to the original recipe, we're going to have to divide everything by 2 to get a total of 5 pancakes. So this would be half of an egg, 3/2 tablespoons of butter, etc., going all the way back. So what I'm saying is we can use our rationale of how ratios work in combination with this definition of stoichiometry for chemical equations to predict if you want a certain amount of product, how much reactant do you put in? If you have a certain amount of reactant, how many products are you going to make? And we can use this analogy of baking pancakes to understand that. Right, so let's just change the form a little bit. Instead of a recipe for making pancakes, let's actually look at a simple chemical equation. 3 parts hydrogen, 1 part nitrogen. Mix these together in a bowl, put them on your stovetop, again, hypothetically speaking, in parallel to our pancakes analogy, to make 2 parts of ammonia. Well, what happens if instead we have 3 moles of nitrogen? Well, all we need to do is look at the original recipe, see that we start with 1 mole of nitrogen. If then we want to have 3 moles of nitrogen here, we would also need 3 times the amount of hydrogen, so a total of 9 moles of hydrogen. And if we mix these things together, we would end up with 6 moles of ammonia. Right? If we scale one thing up, we should scale everything else up because that's how ratios work. However, what if we only wanted 1.3 moles of ammonia? Well, here we can see now we're going to be incorporating some decimals, and it's always the decimals that seem to trick people into thinking that chemical equations are more complicated than baking recipes. They're not. So if we want 1.3 moles of our product, I'm just going to clean this up a little bit again. If we want to scale this down to 1.3 moles of our product, the way that we can predict how much of the other reactants we would need is just by observing, again, the values that are presented here, these stoichiometric coefficients, in our balanced chemical equation. If we want 1.3 moles of ammonia, of this NH3, well, we know that there's 1.3 moles of ammonia per our chemical equation, 2 moles of NH3. And by setting up a simple kind of, cross-multiplying set of ratios, this 1.3 moles of ammonia is going to be equal to however much in this new situation, let's say hypothetically, of the nitrogen we would need. But according to the balanced chemical equation, there is presented here 1 mole of N2. So a 2 to 1 ends up being equal to a 1.3 to question mark, right? That's what the ratio is that we're working with right now. Now, if we solve for the amount of nitrogen that we would need, we're going to take 1.3, we're going to divide it by 2. Technically, we're also going to multiply this 1 mole of nitrogen up to the other side. That just ends up giving us the same number. Our question mark of N2, being again 1.3 divided by 2, is equal to 0.65 moles. So if we only want 1.3 moles of ammonia, we're only going to have to use 0.65 moles of nitrogen. Now, another way that we can think about this, which the secondary example I'm going to use to calculate how much hydrogen we would need in this hypothetical example, it's super useful to recognize that these stoichiometric coefficients out in front of all of our molecules can be used like conversion factors. So if me even just saying that scares you, you don't have to worry about it. As long as you can use your stoichiometric coefficients like ratios in our first example, that's perfectly fine. You will always be able to get to where you need to go. But if you've become very comfortable with conversion factors and you're like, yes, please lay it on me, let me show you the ways. We are going to start with 1.3 moles of our ammonia, 1.3 moles of our NH3. In each of these, again, stoichiometric coefficients in the chemical equation can be used as conversion factors. Like, for instance, there are 2 parts of ammonia per every 3 parts of hydrogen. And the way that this correlates or translates into a conversion factor calculation is 2 moles or 2 parts of ammonia, that's the 3, for every 3 moles or parts of hydrogen. So we're going to be using our chemical formula, our chemical, So we're going to be using our chemical formula like units. So moles of NH3 cancel with moles of NH3, and we can see that we're only left with moles of H2 in the numerator. And this value of 3, again, comes from our chemical equation, just like how the value of 2 comes from our chemical equation. So we're going to take 1.3, multiply it by 3, divide it by 2, and this is going to give us a total of 1.95 moles of H2 necessary in order to make 1.3 moles of ammonia. And in reality, if we wanted to actually physically mix our reactants together to get 1.3 moles of ammonia, we would need both of these calculations, right? We need to mix 0.65 moles of nitrogen, 1.95 moles of hydrogen, and that would give us 1.3 moles of ammonia. But in order to find these values, we had to use stoichiometry, either by using these stoichiometric coefficients as ratios, which we did in the first example here. 1.3 to 2 was equal to question mark divided by 1, or we can use them like conversion factors, which was the second calculation down below, starting with the number that we knew, using our coefficients as a conversion factor, and calculating the number of hydrogen that we would need on the other side. So again, moving forward, whichever of these methods, ratios or conversion factors you are the most comfortable with, feel free to use. Both of these are methods that will get you an answer on the other side. So let's see stoichiometry in action with another chemical equation. This one's a little bit more complicated in appearance, but the process is going to be the same. The only thing really that's different is in this problem we are asked not necessarily how many moles of gallium hydroxide are required to completely react with 8.65 moles of magnesium cyanide. Rather, it's how many grams? Well, in order to find the grams, you will first need the moles. You can start with moles of magnesium cyanide, find moles of gallium hydroxide, use the moles in conjunction with a molar mass to find grams. So we're going to be combining old concepts with new concepts in order to see really the power of stoichiometry and its predictive power. So yeah, I'm going to let you guys work through this problem, see if you can't get it started on your own, then we're going to work through it together. All right, welcome back. We are going to be starting with what we know. We are going to be starting with 8.65 moles of magnesium cyanide, and magnesium cyanide, we can see in the equation below, is one of the reactants. So let's start with this 8.65 moles of magnesium cyanide, MgCN2. And the question is, how many grams of the gallium hydroxide are required? Well, I'm going to solve this problem using the conversion factor method for the coefficients in our balanced chemical equation. The main reason being is it kind of saves us on time in terms of the number of calculations we need to do. So we can see this as I continue the problem right here, right now. So we're starting with 8.65 moles of magnesium cyanide. We're trying to figure out how much gallium hydroxide we also need to work with. In order to do so, we need to figure out, well, how many parts magnesium per parts gallium. We can see in the balanced chemical equation that there are 3 parts magnesium cyanide per every 2 parts, so mole instead of parts, mole, of gallium hydroxide. So at this point in our calculation, we have gotten out of the units of moles magnesium cyanide. We are now in the unit of moles gallium hydroxide. From here, the calculation of how many grams gallium hydroxide is just one additional conversion factor. We need the molar mass in order to find this, specifically the molar mass of the gallium hydroxide, since that's the unit that we are in right now. So we can whip out our periodic table, find the molar mass of gallium hydroxide, and the value of that molar mass is going to be equal to 120.74 grams per every 1 mole of gallium hydroxide. From here, we are now out of the unit of the mole and into the unit of grams gallium hydroxide. So we can take 8.65, multiply it by 2, divided by 3, multiply that by 120.74, and our final answer is 696.3 grams of our gallium hydroxide. So again, if you broke this problem down into multiple steps by using ratios to find the numbers of moles of gallium hydroxide, and then use your molar mass to find this final mass of 696.3, that's perfectly fine. The advantage of using our stoichiometric coefficients as conversion factors we can see here. There's just one string of conversions that we will need to calculate, and that will give us our final answer with, again, just kind of one string of calculations instead of multiple steps. Again, whatever you're the most comfortable with, but I do want to also demonstrate kind of the pros and cons on both sides. All right, so we've seen a couple of problems so far demonstrating the usefulness of our stoichiometric coefficients and their predictive power for determining how much, let's say, reactant we would need. But there are a couple of additional terms that we're going to need to know, namely, if we're looking at the product, right? The purpose of running a chemical reaction most of the time is not to double check the amount of reactant that you needed, but rather to get a certain amount of product because that's what you're trying to make. So let's introduce the term of theoretical yield in connection with our pancake analogy again. So let's say we have our balanced chemical equation, right, our recipe, and we find that, despite how many pancakes we want to make, we're kind of digging out all of these ingredients that we need. Like let's say again, we had that 3 cups of flour. We're like, heck yeah, we can double our pancake recipe. But we only have 1 tablespoon of butter. This 1 tablespoon of butter means that we cannot make all of the pancakes that we want. At most, because we only have 1 tablespoon of butter, in connection with the recipe, we can see, which normally calls for 3 tablespoons of butter, we can only at most make 1/3 the number of pancakes. This means we're also going to need 1/3 of all of the other ingredients, right? If you try and make a pancake, hypothetically, with only 1 tablespoon of butter, but you still want to try and double the recipe, like, your pancakes are not going to turn out very good because you're missing an ingredient. You can only make as much as the least amount of ingredient you have. This means that no matter how many eggs we have, no matter how much baking powder we have, no much flour we have, if we only have 1 tablespoon of butter, we can at most make 3.3 repeating pancakes, or like 3 pancakes and a silver dollar pancake. It doesn't matter how much of the other reactants we have, if there are too many compared to one of the reactants, in this case the butter, where we don't have enough, you can't make more pancakes. This means that the theoretical yield, the amount at most we can make of our pancakes, is going to be 3.3. In a chemical sense, the theoretic yield, also known as the stoichiometric yield, is by definition the maximum amount we can make of a product once all of what is known as the limiting reactant has been completely used up. The limiting reactant is like our butter. Once we run out of the reactant that we have the least amount of proportionally to the rest of our recipe, the reaction can't continue. It doesn't matter how much of all of the other stuff we have in excess. You're done making pancakes once the butter's out. In the reaction we have illustrated below, which is 2 parts hydrogen, 1 part oxygen, trying to make a bunch of water, the reaction will only be able to continue until one of the reactants runs out. Well, since we can see the reaction is 2 parts hydrogen to 1 part oxygen, let's start combining things together. So 2 parts hydrogen, 1 part oxygen can make 1 water molecule. 2 parts hydrogen, another part water or oxygen here to make another water molecule. Here's a 2 to 1. Here's a 2 to 1. And here's a 2 to 1. So it looks like we can only make 2, 4, 6, 8, 10 water molecules, and we'll have 2 oxygens left over. And sure enough, on the right-hand side, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 water molecules from the recombination of everything we have in the correct proportions, and 1, 2 oxygens left over. Now, it doesn't matter that we have these 2 oxygens left over. There is no more hydrogen. So no matter how hard these little oxygen molecules try, they cannot turn into water. There's no other hydrogen around. How can they? So in this reaction, we would conclude that the hydrogen is the limiting reactant. It was the butter to pancake of this reaction, right? Butter is to hydrogen as water is to pancakes. Once we're out of the hydrogen, it doesn't matter how many of the other reactants we have, there's no more water being formed. So when we observe a given amount of reactants, it doesn't necessarily mean that all of the reactant is going to be able to combine together. For instance, if we're mixing 25.7 moles of hydrogen and 8.75 moles of oxygen to create water, we need to know which of these 2 things is the limiting reactant. Also, it's going to pay to know how much water we can actually produce on the other side. Now, it's pretty straightforward to see that the amounts that we have listed here do not exist in a 2 to 1. Because we don't have a 2 to 1, it means that we don't have the perfect combination of reactants. There's going to be something that gets used up first, and there's going to be something else that gets left over. So what we're going to first find is the theoretical yield of our product in combination of identifying the limiting reactant. It's actually, I found a method that's kind of like a 2 birds, 1 stone situation. So I'm going to teach you guys that. As well, once we are done finding the theoretical yield and identifying the limiting reactant, we can also calculate how much of the excess reactant is left over. So let's start with the limiting reactant and the theoretical yield. First and foremost, we are going to need a balanced chemical equation. Fortunately for us, the reaction that we're working with, the hydrogen, oxygen, and water, was just on the previous slide, so I'm going to rewrite the balanced chemical equation here. 2 parts hydrogen to 1 part oxygen creates 2 molecules of H2O. And just like every calculation we have worked with before, we are going to start with what we know. The difference is that we're not going to be performing just 1 simple calculation, we're going to be doing 2 and then comparing the results. So we're going to start with what we know about the hydrogen, 25.7 moles of H2, and we're going to start with what we know about the oxygen, 8.75 moles of O2. Now what we are going to do is take both of these 2 reactants and using stoichiometry, convert the amount of reactant into product. So we're going to start with hydrogen, calculate how much water it would be able to hypothetically make, and oxygen, and calculate how much water it would be able to hypothetically make, assuming that the other reactant is present in the amount that we need. Then we are going to compare the results after. So we'll save that conversation for when we actually have numbers to observe. So let's start with hydrogen. According to our balanced chemical equation, there are 2 parts water produced for every 2 parts H2 consumed. And with oxygen, there are 2 parts water produced per every 1 part of oxygen consumed. The calculation then of how many moles of water could hypothetically be produced from all of our hydrogen is 25.7 moles. And from our oxygen is going to be 17.5 moles. So here we can see, starting from the perspective of each of our two reactants, how much water could at most be made, assuming the consumption of all of the reactant. So what we're going to do is compare these two outputs, and we're going to pick the number that is the least of them. And the reason why we pick the number that's the least of them is this signifies the theoretical yield, the amount that can at most be made up until one of the reactants runs out. So if we compare 25.7 moles of water to 17.5 moles of water, what these two numbers tell us is that if all of the hydrogen gets used up, we can make 25.7 moles of water. However, once all of the oxygen gets used up, we can only at most make 17.5 moles of water. This means that there's a difference, a discrepancy between these two values. And once all of the oxygen's used up, we can't get to 25.7 moles. All of our oxygen will be gone, and the leftover hydrogen's just gonna have to sit around. We could potentially have made up to around 26 moles of water, provided we had enough oxygen, but we don't. The oxygen will run out once we hit 17.5, and all of the rest of the hydrogens are just gonna be hanging out, unreacted, and unable to do anything. So, again, in recap, we start with both of the numbers that we know for the reactants. We calculate how much product we could hypothetically make in both cases, compare the two numbers, and we pick the one that is the least. The value that is the least of the calculations is going to signify the theoretical yield. And the reactant that we use to get to this number is going to be the limiting reactant. The other reactant is that in excess. So we can at most make 17.5 moles of water from the 8.75 moles of oxygen. Once all of that's used up, you can't make any more water even if we tried. So the other amount of water that we calculated is actually just a dummy number. It's a red herring. It doesn't mean anything to us. It's a hypothetical situation that is unachievable because of the limiting reactant. All right, so we can, though, use the number to calculate how much excess reactant is left over. So in order to do this, what we're again going to do is compare the two answers that we calculated, and we're going to find the difference in these values. What's missing? How much water could we hypothetically have made had we had enough oxygen? So we're going to take 25.7 moles of water, right, the amount, the red herring that we just crossed out, and we're going to subtract out the 17.5 moles of water that we actually could make. This is the amount that we made and then production ceased. The difference between these two values tells us the potential of the water that we could have made. How much is missing? Like, what's the gap? The calculation of 25.7 minus 17.5 is 8.2. So there are 8.2 moles of water that we just couldn't make. We have that excess hydrogen hanging out. It would love to make up the difference and create 8.2 more moles of water, but it can't because we don't have enough oxygen. So what we're going to do instead is take this 8.2 moles of water and calculate, well, according to this difference, how much hydrogen is still sitting around. If there's 8.2 moles of water uncreated, it's going to correspond to all of the hydrogen that's left over. So there's 2 moles of hydrogen per every 2 parts, or 2 moles of our water, right, 2 to 2, meaning that in terms of calculation, there's actually still just 8.2 moles of hydrogen hanging out unreacted, would love to make water, but it just can't. Again, there's no hydrogen around. So these 8.2 little moles of hydrogen are just kind of hanging out in the same vessel as the 17.5 moles of water that were created, in much the same way as the picture we just saw. Our excess reactant is going to hang out in excess, unreacted, unable to do anything, and our water is going to be present as well, this theoretical yield of the 17.5 moles of water. So what I would like you guys to try your hand at is, from the starting amounts of aluminum and chlorine, calculate how much aluminum chloride can be made. Which of the two reactants is your limiting reactant? And in much the same way that we just saw, calculate how much excess reactant is left over. The big difference here, aside from the species we're working with, is that everything also is present in grams. Remember, in order to use stoichiometric coefficients, you have to be in the unit of the mole. So this is a huge red flag, a huge warning sign. Your first step is going to have to be to convert things into moles. Once your gram amounts, once your masses are converted into moles, then you can work with the problem in the exact same way as what we saw before. So try your hand, pause the video, give this a go, and then we're going to come back together and compare our work. All right, so just like before, we are going to start with what we know. We will start with 14.89 grams of aluminum in one set of calculations, and we will start with the other hypothetical, the 62.89 grams of chlorine in the other. Our first step is going to be to convert these gram amounts into mole amounts. So let's look on the periodic table, see if we can't figure out how many grams of aluminum there are in every mole. And according to the periodic table, the molar mass of aluminum is 26.98 grams per every 1 mole. Chlorine, since there are 2 chlorine atoms inside of this molecule, we're going to have to look at the periodic table, find the molar mass, and then multiply that by 2. And it turns out that there is 1 mole of chlorine for every 70.91 grams. All right, our next calculation though is to get out of grams of reactant and into out of moles of reactant and into moles of product. Well, in order to do this, we need a balanced chemical equation. So you can either start the problem with a balanced chemical equation, or at the very least at this point, you gotta take a pause and figure out what it is. Well, we've actually already seen what the balanced chemical equation for aluminum plus chlorine going to aluminum chloride is. We balanced this equation during part 1's lecture, so if you would like to see how this equation gets balanced, please go back and check previous notes. But we're going to mix aluminum and chlorine to make aluminum chloride, and the balanced coefficients in front of everything are stoichiometric coefficients. We need 2 aluminums per every 3 chlorines per every 2 aluminum chlorides. All right, so again, if you want to see how this equation got balanced, please go back and either double check through your notes, see if you can't find this equation being balanced, or go back and rewatch part 1 of this lecture. So we need to calculate how many aluminums turn into aluminum chlorides, as well as see, from the chlorine's perspective, chlorine to aluminum chloride. So we're going to use the balanced chemical, or balanced stoichiometric coefficients in the chemical equation to do that. There are 2 parts of aluminum chloride per every 2 parts of aluminum. And similarly, there are 2 parts of aluminum chloride per every 3 parts of chlorine. Last but not least, we are asked to find the theoretical yield in grams. So I am going to actually convert moles to grams for aluminum chloride in both cases right away. So we need to, again, observe the periodic table, find the molar mass of aluminum chloride. There are 133.33 grams per every 1 mole of aluminum chloride, and this is going to be a conversion that's present at the end of each of these conversion strings. So we crunch all of our numbers. In the first calculation, we have gotten out of grams of aluminum into moles of aluminum, out of moles of aluminum and into the moles of aluminum chloride, out of moles and into grams of aluminum chloride. So that's how all of our units here are playing together. So if we take 14 divided by 26.98 times 2 divided by 2, so multiply by 1, and then multiply by 133.33, we end up with 73.58 grams of aluminum chloride. And similarly, if we follow suit with the second set of calculations, we end up with 78.83 grams of aluminum chloride. So we're pretty close here. What may have started with pretty disparate amounts of grams actually turned into a pretty comparable amount of aluminum chloride, but only one of these calculations gives us the true theoretical yield, and it will be that which gives us the lesser amount. So the lesser amount of our aluminum chloride, this 73.58 grams, this is the maximum amount we can make. Once we make 73.58 grams, all of the aluminum gets used up. This means that we will have a little bit of chlorine in excess, and we will never be able to reach our true potential. We will never be able to, I can't even say true, we'll never even be able to reach our maximum potential. There we go. We cannot get up to 78.83 grams because the aluminum gets used up. So the 73.58 grams of aluminum chloride, this will be our theoretical yield. And the aluminum, the corresponding reactant that gave us this calculation, will be the limiting reactant. Oh no, I think my pen might be dying. We'll wrap this up quickly. All right, so the chlorine that is left over, therefore, is the excess reactant. And this excess reactant is going to, again, just kind of coexist with the aluminum chloride once all of the aluminum is gone. The question is, how much chlorine do we have left over? Well, just like before, we're going to take the hypothetical amount that we could have made and subtract out what we actually made. So we're going to take 78.83 grams of aluminum chloride. Again, we have to keep track of what formula we're actually, paying attention to, what we're working with. And we're going to subtract out 73.58 grams of aluminum chloride, and this is what we actually made, giving us a difference of 5.25 grams, again, of aluminum chloride. Now what we're going to do is use this value of the aluminum chloride and calculate backwards how much chlorine must be left over, how much excess chlorine is hanging out that could not make up the difference, that cannot be used up to make an extra 5.25 grams of aluminum chloride. So we're going to start with that 5.25 grams of aluminum chloride. I'm just laughing at my pen. I don't know if it's actually picking up on the capture, but it is getting real janky. So the 5.25 grams of aluminum chloride, we are going to now reverse engineer. We're going to turn this back into moles by dividing by 133.33 grams for every 1 mole. We are then going to use our stoichiometric coefficients to get out of aluminum chloride and back into chlorine, where there are 3 moles of chlorine per every 2 moles of aluminum chloride. Again, it's just my pen. That's why I'm laughing. And then we're going to, last but not least, get out of the unit of the mole and back into the unit of the gram, since it's the gram that we are being specifically asked to find. And there are 70.91 grams of chlorine per every 1 mole of aluminum chloride. We're just so close to the end. Otherwise, I would pause and get some more batteries, but we're so close. Okay, so we complete the set of calculations, and we would predict that there are 4.19 grams of chlorine left over that are unreacted and hanging out, again, in the same vessel as the theoretical yield that we were able to produce. All right, so there are so many other forms that this problem can take. We just worked through two of the examples that are the most common, starting with the amount of reactant you have and finding the theoretical yield of product. We've also seen how to find the amount of excess that is left over. If you've seen problems like this in high school and you learned a slightly different method, that's totally fine. The textbook also illustrates a couple of additional example problems pertaining to how we can use stoichiometric coefficients. Again, totally fine. Get as much practice as you can. Find as many different perspectives as you can. Find the problem-solving method that works best for you. Having said all of that, be expecting to see other types of problems in this vein. Your goal is always going to be to get into the unit of the mole and then use the stoichiometric coefficients to kind of bounce around, to go from reactant to product, product to reactant, reactant to reactant, or product to product. Either way, you are going to be using the stoichiometric coefficients as either ratios or conversion factors to change your perspective. What are you trying to pay attention to? What are you trying to calculate? Always be critically evaluating what you have versus what you're trying to find. The last term, though, that we need to introduce is what is known as the actual yield of your pancake. This is also going to connect then to the percent yield of your pancake. And this, again, is going to be a good example for stoichiometry. Let's say, like, again, you thought you were going to be able to make, like, 20 pancakes, but it turns out that you only had 1 tablespoon of butter. You're like, ah, crap, I can only make 3.3 pancakes from this 1 tablespoon of butter, and all of the other coefficients adjusted also due to this limiting reactant situation. And you mix in the batter, and you spill half the batter. So sometimes things happen in labs, sometimes things happen in the real world, sometimes things don't go according to plan. If you run into the event where you spill half your batter or you spill half of your reaction on the benchtop in lab, you're not going to be able to get even up to this theoretical yield. You're going to be missing stuff. Right, so if in this situation you spill half the batter, at most you're going to be able to make, oh man, what is that? Like 1.3 divided by 2 is 1. It's gonna be like, what, 1.6? We're just gonna roll with it. It's gonna be around 1.6, 1.5, a little bit over 1.5 pancakes, but that's gonna be it. So like, if you were honestly hoping to make 20 pancakes one day and you only ended up being able to make 1.6, I'd chalk that up to being a bad day. But again, sometimes things just happen in the lab and sometimes you don't have everything that you need, or even if you do, mistakes happen. So how can we, as good scientists, instead of making up numbers or instead of trying to create a false report, how do we actually acknowledge what happened? Well, this is why we have two different terms for theoretical yield versus actual yield. The theoretical yield is what you in theory hoped to make. The actual yield is what you actually made. And so if we connect the actual yield, which is, again, the amount of product you actually obtained, which is more than likely going to be less than the value of the theoretical yield, if you combine this with the theoretical yield, we can calculate what is known as a percent yield. This is going to relate the actual and the theoretical by taking a fraction of what you actually obtained divided by what you hoped to attain. Now again, because the actual yield will often be less than the theoretical yield, when you multiply this by 100, you will end up with a percent. So actual yield and percent yield are oftentimes used in tandem, particularly when reporting values in the literature. So if someday you're a scientist working on synthesizing a great big new product, and you're reading through the literature, previous publications, seeing what other people have done, you're more than likely going to see a number of actual yields and percent yields. In using the equation presented here, then, you can calculate what their theoretical yield was, how many reactants they used inside of the reaction, and you can help or hope to like recreate that research and then build up on top of it. So our last calculation of the day is, let's say 0.58 moles of sodium and 0.35 moles of fluorine are mixed in the lab but only 0.1 moles of sodium fluoride was actually recovered. What were the theoretical yields and percent yields of the sodium fluoride that you made? So I hope you pause the video to attempt calculations by yourself, but this is our last problem of the day, so let's come back together one more time, compare our answers, and then call it a chapter. So we are given some amounts that were mixed together. 0.58 moles of our sodium, as well as 0.35 moles of our fluorine. Well, in order to convert, because we can see that we're already in the unit of the mole, molar masses are not needed here, we need to figure out how to convert sodium to sodium fluoride, as well as fluorine to sodium fluoride. We're going to need a balanced chemical equation. So if we mix sodium and F2 together to create some NaF, what are the balanced coefficients that we are going to need? Well, in a really straightforward way, we can see we have 2 fluorines on the left, which means we need 2 fluorines on the right. And now that we have 2 sodiums on the right, we're going to need 2 sodiums on the left as well. So this is a really straightforward equation to balance, and now we can see what the stoichiometric coefficients are that we are working with. So let's convert sodium into sodium fluoride, where there are 2 parts sodium fluoride for every 2 parts of sodium. And there are 2 parts of sodium fluoride for every 1 part of fluorine. This means that, according to the first string of calculations, we at most could make 0.58 moles of sodium fluoride. And according to the second set of calculations, we at most could make 0.70 moles of sodium fluoride. So this is an excellent lesson. Just to take a brief pause, if we observe the molar amounts that we started with, it appears as though we had more sodium than fluorine, which is technically true. But if we take into account the actual balance of necessary stuff in, or according to the chemical equation, we actually have an excess of fluorine. Right, according to the calculations that we just did, where we take the lesser amount, and this is our theoretical yield, we can only make 0.58 moles of sodium fluoride before the sodium runs out. This means that we have excess fluorine. There is too much fluorine, even though there is a lesser amount absolutely of fluorine than sodium, because of this 2-to-1 ratio that is necessary to make sodium fluoride. We're gonna run out of the sodium first, right? It literally, or according to the balanced chemical equation, we literally need 2 times as much sodium than fluorine, and we don't have that when observing the molar amounts that we're starting with. So the 0.58 moles of sodium fluoride will be the theoretical yield. Fluorine is going to be our excess reactant. Now, we're not asked to find here how much excess is left over, so we don't have to do anything with any of these numbers ever again. We have found the theoretical yield. Last but not least, let's find the percent yield. Since we are told that only 0.1 moles of sodium fluoride was actually recovered, we are going to take that 0.10 moles that was actually recovered, divide it by the 0.58 moles that we in theory could have made if we actually maximized our production. We're going to multiply that by 100. This is going to give us a percent value equal to 17. So from start to finish in this problem, we had so much reactant, we wanted to make so much product, but we were only able to even make 17% of what we were hoping for. This is how what a percent yield is. And with that, we are going to wrap up chapter 8. So today we have talked about stoichiometry as well as limiting reactants, theoretical yields, actual yields, and percent yields. And the parallel that we kept making was to pancakes. It's a pretty delicious analogy, if I do say so myself. But if at the end of the day you have trouble kind of wrapping your head around what stoichiometry means, definitely do try to put yourself back in the mindset of thinking of this like a recipe. All of these numbers are ratios. If we scale one up, we have to scale all up. If we scale one down, we have to scale all of them down. And so long as we are scaling appropriately, we can also interconvert using these ratios, as well as treating them like conversion factors. All right, so feel free to work on these example problems. If you have homework, please do your homework. And until next time, class is dismissed.